Next speaker is Prajwal Thool, and he is a senior scientist at the Small Molecule Pharmaceutics group at Genentech, SMP. He has high interest in pediatric formulation development and also powder flow, as well as investigation of formulations. And obviously here we'll talk about how to investigate a tablet through analytical tools that are available. That's really interesting way. Sometimes things happen, and you have to investigate for a GMP deviation or whatever or changes. Having these tools available certainly helps us to get conclusions faster. Again, thank you, Prajwal.
Thank you, Feroz. Thanks to the organizers for the opportunity. I hope you can hear me okay. So the oral viability of the tablet dosage form, as you know, represents how effectively a drug can enter the systemic circulation. And for an immediate release tablet dosage form, achieving optimum bioavailability is dependent on two steps. Number one, the tablet disintegration, and number two, the drug dissolution. And although both tablet disintegration and dissolution processes are extensively studied and their mechanisms well understood, however, the first step, which is the water ingress or water permeation or water transport, and I'm going to interchangeably use these words, or percolation, is not well understood. And this knowledge gap hinders our ability to develop drug products rationally. So my talk for today will help overcome this knowledge gap to enhance drug delivery. So the agenda for today's talk is basically be covering three aspects. The first aspect would be to experimentally deconvolute water transport into the tablet, and we do this using a simple device that we conceptualize at Genentech. The second aspect would be to study the microstructures of tablets and to gain microstructural insights to understand how water is transported into tablets and why certain membranes behave differently using advanced imaging techniques. And we do so using three different imaging tools, first being focused ion beam scanning electron microscopy, mosaic field view scanning electron microscopy, and 3D X-ray microscopy. And we do this with our collaboration with DGM, which is a company based out of Boston. And lastly, we use advanced computational and AI techniques to quantify parameters that govern water percolation behavior. So this is a schematic which explains what percolation is. I'm not going to go into the details, but generally speaking, percolation is a fundamental behavior that is demonstrated by all porous materials. And it describes the fluid movement inside the porous materials under the influence of gravity and capillary-induced forces. For tablets specifically, for water absorption, the composition of the material is extremely important. So if we have hydrophilic materials, it enhances water absorption, and porosity helps enhance the distribution of the water in the tablet matrix. So Washburn equation is typically used to measure the capillary flow of fluid through the porous media. So the length or the distance traveled by the liquid front inside the porous media is directly proportional to the mean effective pore radius of the solid. It is directly proportional to the surface tension of the fluid and the contact angle of the solid-liquid interface, and it is inversely proportional to the viscosity. So in summary, for a fluid to travel efficiently through a porous material, if a fluid has high surface tension and a low viscosity, and if the solid has high porosity and high hydrophilicity, it efficiently transfers water through the porous material. So let's take a real-life example to understand why studying percolation is important. And this is an example that we had encountered recently, where an immediate release tablet dosage form containing a highly water-soluble drug substance that was manufactured using high shear wet granulation process using the components that are listed here in the table. So it contains microcrystalline cellulose as a diluent, hydroxypropyl cellulose as a binder, and cross-caramelous sodium extragranularly as a disintegrant. So during our testing, dissolution studies, we see that even after 20 minutes of dissolution, the core of the tablet remained dry. So this is highly unusual for an immediate release drug product containing a highly water-soluble compound with optimum amount of disintegrant. So this clearly indicate that the lack of tablet disintegration and poor dissolution is attributed to poor water uptake. So this underscores the importance of studying this often overlooked aspect. We did some iterative formulation development, and not so scientifically, I would say. The first thing that we did was we just doubled the concentration of the disintegrant, hoping that it may overcome the issue. However, after doubling it, so now from 4% to 8%, we don't overcome the poor water uptake into the tablets. So subsequently, in our quest, we leveraged the principles guided by the Washburn equations, and we wanted to understand what kind of materials can help us overcome this poor water penetration problem. So to do that, we tried to leverage the most highly hydrophilic materials available, and that were attributed by the contact angles. So we evaluated dicalcium phosphate, which has a contact angle of 0 degrees, which indicates that it is highly hydrophilic material, meaning that it has a capacity to enhance water uptake through the pore. Subsequently, we also evaluated mannitol and spray-dried lactose, and finally, Avicel with a contact angle of about 55 degrees should have a lower water uptake when compared to DCP. Surprisingly, when we do the disintegration studies, we see that MCC, although has had the highest contact angle, demonstrated the best tablet disintegration performance. So this clearly suggests that there are more attributes than just hydrophilicity of a material that is at play, and we clearly don't understand what leads to an optimum water uptake into the tablet. So we wanted to do a systematic and structured study, and we do this in a very simple manner. And what we wanted to do is why MCC and DCP behave very vastly different from each other. So to understand that, we made pure MCC and DCP tablets using trace amounts of magnesium stearate as a lubricant to aid in tablet ejection. And the tablets were manufactured using a tabletop tablet press, and all the tablets were manufactured using 6 millimeter round flat face tooling at a given solid fraction. And the thicknesses were kept constant so that we could compare the two, apples to apples. And the thicknesses were kept constant by varying the tablet mass because the densities were a little different. So in order to deconvolute the water ingress that we would typically encounter in a dissolution or disintegration bath, we wanted to understand this mechanism, and we wanted to do this without damaging the tablet integrity. For that, we had to manufacture a device, and we conceptualized this very simple device at Genentech, and it contains 3 simple components, as shown here in this cartoon. So it contains a fluid reservoir where the fluid is housed, and that fluid reservoir also doubles up as a housing for a capillary tube. The capillary tube, how can I play this video? I have a small video, I think. Okay, great, thanks. So the capillary tube helps convey water that is present in the fluid reservoir into the tablet, and the water uptake can be measured using an analytical scale at predetermined time intervals, and we added trace amounts of blue dye to help better visualization. So after having the method ready, we evaluated the pure DCP and MCC tablets. So on this slide, we see the water uptake for pure DCP tablets, 2 key takeaways. Here, the tablets were manufactured at 3 different solid fractions to yield 3 different porosities, ranging from 0.15 to 0.25. Number one, very surprisingly, we don't see any changes in the behavior or the volumetric expansion behaviors of the DCP tablet. The tablet remained rigid from before the experiment and after water percolation study. This suggests that the water transport into the DCP tablet occurs through the pores. And number two, the water uptake, the amount of water uptake through the DCP tablet increases as the porosity increases. So this suggests that for DCP tablet, the water uptake only runs through the pores. And if the tablet lacks pores, if the tablet is compressed at very high compaction forces, then we hinder the ability to transfer, or we hinder the DCP's ability to uptake water, and that may result in poor disintegration and dissolution performance. A similar study was done for DCP to compare how does it compare to the DCP, a pure DCP tablet. And in case of MCC tablet, the tablet was compressed at much higher solid fraction, which yielded very low porosity. So even at very low porosity, we see a substantial increase in both the total amount of water uptake and also the rate at which the water is uptaken. And this was highly unusual because DCP has has a contact angle of 0 degrees, which represent that it is highly hydrophilic, whereas MCC, on the contrary, has the contact angle of about 55, which in comparison is not as hydrophilic. So we wanted to understand why MCC behaves this way over DCP. The second observation that we also saw was the volumetric expansion of MCC tablet before and after the water uptake study. And we believe that as the water is ingressing into the MCC tablet and as it is volumetrically expanding because of swelling behavior of MCC, it's creating more pores, and that is helping facilitate more ingress of water into the MCC tablet. And this may perhaps suggest why we saw such enhancement in the disintegration performance in the earlier case study. So we wanted to understand the microstructural aspects of both these tablets to sort of tease out why these two tablets behave the way do in terms of their water uptake capabilities. So the first technique that we leveraged is called mosaic field view scanning electron microscopy, and this work was done in collaboration with our colleagues at DGM. So it's a simple SEM technique with some additional capabilities. It involves 3 broad steps. The first is to mechanically cut the tablet to expose the cross sections. And once the cross sections are exposed, then subsequently using ion beam, the cross sections are polished to remove any rough surfaces. Second step involves imaging, and this is similar to a traditional SEM imaging. However, it differs mainly as in a series of SEM scans are taken and then they are stitched together to form a tile or mosaic, which results in very high resolution without losing any detail. And the third step that we leverage is the segmentation analysis to understand the microstructures of the tablets. Here is a depiction of the MVF SEM scan of a binary tablet containing the DCP and MCC components. And as you can see, we see very distinguishing features of the DCP and MCC tablets. And using this technique, we can tease out any volume fractions or any spatial distributions so as to understand why the tablets are behaving the way they are. So here is the first MFE SEM scan of the pure DCP tablet. The image on the left is the original MFE SEM scan, and what we see is DCP particles are highly dense and they lack any kind of pores. And secondly, we see a formation of a lot of fractures, and we believe these fractures are attributed because of the brittleness of DCP upon compaction. So we did segmentation analysis of DCP tablet, and what we see is the pores are found to be highly localized. They're also non-homogeneous, and they are locally distributed. And because of this, we believe that DCP tablet has very low water uptake in comparison to the MCC tablets. A similar MFE-SEM scanning was done on pure MCC tablets. So the image on the left is of the original MFE-SEM scan. And what we see is MCC is highly coiled microstructure. And we don't see the formation of cracks that we had seen with the DCP tablets. And we believe that is because of the plasticity attributed to MCC. Segmentation analysis revealed that there was a uniform distribution of interconnected particles of MCC. However, we don't see formation of any pores on the MCC tablets. So this clearly doesn't help us understand why MCC tablets had such high and rapid water uptake over DCP tablets. So we went back and did some segmentation analysis of the binary component tablet comprising of DCP and MCC. And what we see is the pores that were attributed to the DCP, which are depicted by the purple region. The pores are highly localized, which we were able to tease out from the original DCP MFV scan. And in case of MCC, which is depicted by the green domains, we don't see any formation of pores. And also, like I said earlier, these pores are highly localized and they are not connected to each other when pertaining to the DCP tablets. So we did a literature survey to understand how does MCC enhance water uptake. And what we have come across is MCC is highly porous. However, these pores are only resolved at a nanoscale. And so we need some other techniques other than imaging. And so the literature review suggests that these pores are only be able to resolve using techniques such as mercury porosimetry or nitrogen gas adsorption techniques. And these pores happen to be in the orders of less than 10 nanometers. And clearly, the lack of pore resolution on MFE-SEM scan is attributed to the limitation of this imaging technique. So we wanted to explore if there is any other imaging technique that can help us visualize these and gain these micro insights of these tablets. So we leveraged another technique called focused ion beam scanning electron microscopy. This is similar to conventional SEM. However, it differs in the way that for conventional SEM, we use electron beam for imaging, whereas here an ion beam is used, typically gallium, and which results in a very high resolution picture that can resolve nanoscale microstructures. So what we see here is for pure DCP particle, the particle is highly dense and it lacks pores, which we were able to also see from MFE-SEM. But in case of MCC, we were able to see these numerous pores that were inherently attributed to the MCC particles. And these pores run parallel to each other like tubes. And we believe that because of this, the water uptake rate is rapid. And because of the nanoscopic parallel tubes, it is also helping drive water uptake through capillary-driven forces. So if MCC, in fact, is helping enhance water uptake due to the presence of these nanopores, then we want to understand at what levels of MCC we are able to overcome the poor water uptake and resolve the poor disintegration and dissolution performance attributed to our model compound. To do that, we did a systematic and structured study to compare the water uptake kinetics between these different model formulations, and B, understand at what concentrations of MCC we can achieve optimum and desirable quality attributes of the immediate release tablet. So the DCP tablets, pure DCP tablets, were spiked with 5 to 30% of MCC, and all the tablets were compressed at 0.85 solid fraction, and the thicknesses were maintained constant. So we went back to the water uptake studies, and what we see is addition of as little as 5% MCC dramatically doubles the water uptake rate, and the uptake kinetic proportionally increases with an increase in the concentration of MCC. So this clearly may help us understand that maybe MCC, because of the nanopores, is able to form this interconnected network, which is helping enhance the water uptake into the tablet and is able to overcome the poor tablet disintegration and dissolution performance. So we wanted to understand the interconnectivity of the MCC in the DCP containing tablet. And for that, we leveraged another imaging technique. Here is, it's three-dimensional X-ray microscopy. It's, compared to, the mechanism is similar to a conventional, medical CT or micro CT. However, the major difference is in the resolution. For a conventional micro CT, we are able to resolve images in the orders of 10 to 100 microns per pixel, whereas for the three-dimensional XRM, we are able to resolve images in the orders of 500 nanometers per pixel. And there's also a non-destructive and a non-invasive technique. So we can directly take the tablet specimen, put it on a stage, and we can take a lot of 2D radiographs in the orders of hundreds to thousands of images. And using iterative back algorithms, we can stack these 2D images together to create a 3D volume view. So shown here on this is the, oh, I'm so sorry. Can you please play the video? It's on the top right, yes. Yeah, so what it does is not only is it able to help us understand the microstructures at a very high resolution, but also the image contrast is extraordinary. So shown here is the gray scale spectrum and the white scale spectrum on the spectrum scale. And the white scale spectrum typically represent materials of high density, and in this case, it is DCP, whereas the dark scale regions on the spectrum represent lower density materials, in this case, either MCC or pores or air. And so this technique is incredibly amazing to view this interconnectivity of the components. And what we see here is on the top panel, the original 2D scans of these images containing 10 to 30% MCC. And the bottom panel is that of the segmentation analysis. And remarkably, even with 10% MCC, we see this incredible interconnectivity of MCC network within the pure DCP tablet. And as the concentration increases, the interconnectivity increases substantially. So we wanted to visualize the interconnectivity, and for that we did this 3D rendering. The image on the left depicts a DCP tablet containing 10% MCC, and to create this striking visual contrast, we used these two different colors. So the one in blue represents DCP, and the one in green represents MCC. So I want to understand how is MCC distributed within this matrix and is able to help enhance this water uptake. To really appreciate the intricate network formed by MCC, we carefully removed or peeled off the DCP region from the tablet. And what we see on the right is the tablet containing just 100% MCC. And even with 10% MCC, we see this incredible interconnectivity, and that is attributed because of its low density. Can you please play these videos? Yeah. So as you can see, the left-hand side depicts the original DCP containing MCC tablet, and on the right is when you carefully remove the DCP. It's just pure MCC that is distributed in that binary compact. And even with such little amount of MCC, it is able to create this incredible network, and that is able to enhance the water uptake. So finally, we use some computational techniques to help us quantify the parameters that help us understand why MCC containing tablets are helping enhance water uptake. And the first parameter that we evaluate is tortuosity. So tortuosity is essentially a ratio of the actual path length traveled by the fluid inside a porous media to the straight line distance between the porous material. So the cartoon on the right shows that if, for example, a fluid has a convoluted path, And if this is the actual straight line distance between the two, you just take the ratio of these two. And if the ratio is equal to 1, then we say that the fluid travels through the porous material in nearly straight line. And as it is closer to 1, we say that the path length is nearly direct. So even with 10% MCC, the tortuosity value was closer to 1. And as the concentration increases, the tortuosity values decreases, which means that with an increase in the concentration of MCC, the fluid path length traveled is nearly direct from one end to the other end of the tablet. Next, we wanted to understand the efficiency of water transport, which can be quantified by permeability, and this was quantified for the MCC network that was evaluated from the 3D microstructures resolved by the XRM imaging. So permeability is an indication of the flow resistance of the fluid in the porous media, and this was done in 2 steps. In the first step, the Navier-Stokes equation was solved to obtain the fluid velocity and also the fluid pressure. And the second step, Darcy's law was used to evaluate the permeability rate constant. What we see is with an increase in the concentration of MCC in the pure DCP tablets, the permeability rate constant increases linearly, as can be shown here. And that's the reason why we see an enhancement in water uptake for tablets that are admixed with higher concentrations of MCC. So this underscores that for materials that are hampered with poor water uptake, adding materials like MCC can help overcome poor tablet disintegration and dissolution issues, and perhaps help achieve optimal bioavailability. So so we finally went back to the drawing board to sort of overcome this poor disintegration problem that we had encountered. And applying the principles, what we did was we removed all that hotspots that we did earlier. So we went back to the drawing board. The original formulation that contained 4% cross-granular sodium, we took that and we started adding extra granular MCC. And we made 3 prototype formulations containing 10, 15, and 20% MCC. And we manufactured these tablets using high-shear wet granulation process. And all these tablets were manufactured at 3 different tensile strengths. And what we see is with the addition of with the addition of as little as 15% MCC, we were able to get to a disintegration time of 1.5 minutes when compared to more than 20 minutes that we observed earlier. So this clearly depicts that for tablets that have poor tablet disintegration issues, and where water uptake is one of the underlying issues, we have to systematically and rationally evaluate the problems and find solutions using rationally. So in conclusions, nanoporous materials like MCC enhances water uptake, and it is done by wicking. And this forms a highly interconnected network, and it doesn't take a lot of material to do it. And not always, hydrophilic materials like DCP are optimal for water uptake. And advanced imaging techniques and segmentation analysis help us gain microstructural insights of the tablets, which can help us deconvolute the water uptake, behaviors of different matrices. And finally, using computational tools, we are able to quantify water uptake through parameters that drive them, like tortuosity and permeability. So I'd like to acknowledge all my colleagues and our collaborators at DGM for helping us, overcome one of our problems. And with that, I'd like to thank you for your attention, and I can take any questions you may have.
incredible use and visualization of the 3D X-ray and mechanistic understanding. I guess my question is twofold. One, are you only identifying the DCP versus the MCC because of elemental differences in the, like how is this applicable to carbon-only based excipients?
Yeah, I mean, it's a great question. And I mean, for us, the reason we had evaluated MCC and DCP, of course, as you said, like, you know, one of the things is like the contrast that it actually presents, which is easy to sort of understand the microstructural insights. But I believe, you know, and DGM is an expert in that area, and they're trying to sort of, you know, enhance their understanding for other, you know, components which may have difficulties, you know, understanding the microstructures. But I think the power really is not in the imaging; it's in the segmentation analysis. So they have this I2S system which has incredible power to sort of, you know, delineate any kind of, you know, maybe intricacies that we may not be otherwise able to understand through just, you know, qualitative through imaging techniques.
This reminds me a lot of dispersions and domain sizes. And so I don't know if you work with Joe and the other Karthik on this, but have they looked into solid state NMR to determine domain sizes?
I don't know. But yeah, we have a lot of projects ongoing with DGM, and I think maybe they are.
We should talk later.
Sure. Thank you for those questions.
Hi, thank you for the presentation. The literature shows that there's kind of a magic ratio of MCC to DCP typically for oral solid dose, like 70-30 typically what you'd see. And you rely on the MCC, right, for plastic deformation and the DCP for the brittle fracture component to expose unlubricated surfaces to make a hard tablet. Did you take a look at any of the other either cellulosic components like cross-carmylose sodium as like a wicking agent or starches as a swelling agent to improve or affect, I guess, the water uptake in your tablets? Was that part of your study at all?
I mean, the reason why we selected DCP and MCC to begin with is to really, you know, bring some rationality to, you know, solving some of these problems, as opposed to just maybe, you know, doubling the concentration of a disintegrant. And so, as I said, like going back and leveraging Washburn equation, I mean, it states that, okay, if you use components that are highly hydrophilic, and as suggested by the contact angle, DCP is highly hydrophilic because it has a contact angle of 0, which means that water should, you know, immediately wick through, but we don't see that. And MCC, although, you know, which has a contact angle of 55, you know, not as much hydrophilic, it has this, you know, incredible capacity to sort of, you know, help enhance water uptake. And just wanted to start, you know, the fundamental understanding, and eventually perhaps, you know, there could be a time, and if there is a requirement where we have to study cellulosis or any of the other polymers, then yeah, we will. But going back to the disintegrant question of cross-carmylose sodium, just by doubling the concentration of the disintegrant will not help, because it's not that the disintegrant is not doing its job, it's just that water is not percolating into the matrix. So once it does, then perhaps, you know, maybe the disintegrant is going to do its job by swelling or whatever the mechanism it is. Yeah. Thank you.
Hi, nice presentation. I just have one question, maybe related to modified release. So let's say when you, the concept of the percolation and the porosity, right? So when you add like a high viscosity polymer to a matrix and compress it, do you think the whole concept still holds true? Because partially the polymer would be coating microcrystalline cellulose particles. Just want to pick your thoughts on it.
I didn't follow through your whole question because I was hearing some ringing in my ear. So if you could repeat it again.
Sure. So let's say everything discussed works great for IR formulation, right? If you want to make a modified release formulation and you add a polymer and make a matrix out of it. So the drug, the polymer is sort of coating these microcrystalline cellulose particles, right? So do you think the whole porosity concept would still hold true?
Yeah, I mean, good question. And so essentially what we are saying is, not just porosity, not just the hydrophilicity of the material, but, if at all, if you have to enhance this water wicking into the matrix, and if, for example, if your modified release, polymer or the tablet as such is, undergoing, poor disintegration because of, water uptake. And in our case, we have hydroxypropyl cellulose as a binder. And addition of extragranular MCC, perhaps, help wick water. And what we have seen is, and as I have shown in the visual, it actually helps wick water, rapidly. And the experiment that I was showing, it's unidirectional water uptake. But in an actual scenario, when you actually drop the tablet in the physiological media, it is surrounded by water throughout. So the water uptake is going to be multidirectional, and I'm sure that it is also going to help, depending you have adequate amount of MCC. Because on the last slide I showed that when you range, when you vary the concentration of MCC extragranularly from 5 to 20%, you need to find what is the inflection point at which you get that, the interconnectivity of MCC that is helping drive water into the matrix. So yeah, it may apply.
Thank you.
Any other question? Otherwise, time for break, yes?
We're exactly on time.